Hey everyone, welcome to this video on the conservation of energy. I know that we didn't get to this during quiz section, so I just wanted to make a video describing how the conservation of energy formula is derived, just the bare bones behind it, and just walking you through how this works. So let's get started. So the conservation of energy, here is the general bare bones statement. And this is something that we've seen routinely with our conservation of mass and conservation of momentum equations, right? So we have a rate of accumulation, and this time it's on energy. So we have the rate of accumulation. What goes into that is we have the rate that the energy enters the system, subtracted by the energy that leaves the system. And then we have a rate of energy of production within the system. So let's kind of dive deep into each of these different parts and kind of the math behind each one. So let's start with rate of accumulation. So to define rate of accumulation, we simply use dE over dt. So capital E denoting energy. So we have the change in energy over time. And this is just another way to write this out. But essentially, there are three types of energy. So we have kinetic energy, and then we have our potential energy. So for example, gravitational potential energy. And then we have our internal energy. So these are the types of energy that we are looking at. Now, simply, we're just going to write dE over dt right down here. So let's keep going. We have the rate energy that enters the system, and then we have the rate energy that leaves the system. So to define this, we use this entire part right here. So let's start with QS. So QS is basically either or both the heat added to the system through the surface, and also the heat added in the inlets and outlets via conduction or radiation. This is not convection. Conduction is different from convection. So please keep that in mind. Convection is where we are talking about bulk flow. Conduction is kind of the movement of heat. Great. So let's talk about the second term right over here. This is the net energy added in the inlets and outlets. So notice I said net here. This includes energy going in and out via convection, which is bulk flow. And this is through the inlets and outlets. And this negative sign right here is essential because it makes sure that the energy is added to the system. What that means is it just makes sure that the sign is correct. It's the sign meaning positive or negative, right? So let's take a deeper look into this negative right here. As we can see, we have the direction, the normal vector right here. We also have the velocity vector, right? So if we take a look in our system, we have the velocity vector going this way, and we have the normal vector going this way, surface normal vector, then we're going to get a negative value on this side. And on this side, when the normal vector is going out this way, and then we have our velocity vector going out this way, this is going to be a positive energy. But that's not correct, right? We have energy entering the system through this way. We have energy exiting the system. So to make sure that our signs are correct, we're adding this negative sign right over here. And it ensures that the energy is added to the system or subtracted from the system, respectively. Great. So we have this whole term right over here that we just talked about. This is the energy, right? Great. So we have our three different types of energy. As we just talked about earlier, we have the internal energy, we have kinetic energy, and we have potential energy. And all of these combined make up the total energy right over here. So just really briefly, the internal energy right over here, this is just the heat capacity per unit mass. This is just the change in temperature absolute to reference. We have kinetic energy right over here, velocity squared over 2. And then lastly, we have potential energy, and that's just the acceleration due to gravity g times the height, the relative height. So these are all things that we do know, and they all make up this energy, total energy for our conservation of energy statement. So combining all of these terms, we are actually going to keep internal energy and potential energy just as is. And we're going to keep the kinetic energy out right here. So by combining these terms, we can actually come to this. This is actually a part of the final conservation of energy statement. And as we can see, we have it all nestled in right over here. Everything here, as you see, is just this E right here replaced with these more specific types of energy, right? And then now the question may be, what is this term? Where is this term coming from? Is it another type of energy? Well, no, we defined our energy as our 3 types, right? So I'll actually get into this more in a second, but know that this is not a type of energy. These are our types of energy, right? Great, so we just talked about the rate energy that enters the system and leaves the system as described right over here. Now let's talk about the rate of energy produced within the system. Great, so for the rate energy produced in the system, we have 2 terms. We have Qgen, generation. It's all the rate of the heat generation within the system. Great, and some of those processes, we'll actually get more into this in a second. And then we have minus W dot, and that's the rate of work done by the system on the surroundings. And please note that it's the system onto the surroundings. That's why we have this negative right over here, negative work, right? So let's go into each of these terms. So we have Qgen, which is the rate of heat generation within the system. So this includes several things. Some of the key ones are the metabolic heat generation from chemical reactions. Another one is friction. And then another one is this radioactive decay. So this is where heat is generated in the system with several mechanisms. Great, and now let's get into work. So work, pay close attention because we're going to do a deep dive on this right now. But W dot is the rate of work done by the system on the surroundings. So how do we define work? Well, work is also equal to the surface integral, right? This is a surface integral right here, ds, s, surface integral of, we have right over here first, let's do what we do know. We have the fluid velocity right here. And then this right here is actually the force per unit area. And that is applied by the fluid to the surroundings. So this is how we define work onto the surroundings, the system onto the surroundings. Now, if this fluid is causing part of the surroundings to move, one thing could be like the rotation of turbine blades on a wind turbine. We would actually, so this is the same thing moved up, we would actually divide this work right over here as we define into 2 parts, 2 key parts. And we'll also actually go into these 2. So Ws dot is the rate of work done by the fluid to the moving boundary. It's also referred to the shaft work rate. So that's defined by the S shaft. So this is the work rate of work done by the fluid to the moving boundary, right? So what about this term? What is this term? So let's actually go into that. So this term, which is part of our work, right, in the system, is the rate of work done by the fluid at each inlet and outlet. It's a summation, right? So there can be many inlets and outlets. So this is the rate of work done at each inlet and outlet by the fluid. Great, and right here we have the velocity of the fluid. We have the same force done by the fluid per surface area. And then we have over the area, right, of which work is done. Great. And then with these, the most important forces to consider at the inlet and outlet are the pressure forces and frictional forces. And there are also other electrical or magnetic forces right now, but for now, we are going to really focus on the pressure force. So this is defined as the pressure force. So the rate of work done by the fluid at each inlet and outlet for the pressure force. So we have velocity right here, and then we have the pressure And we also have the normal vector and the cross-sectional area where work is done. So in summary, we have right here, as we defined earlier, the shaft work rate. If you missed it, let's go a couple seconds back. I just described this. And then we have this term right over here, which actually is defined for us as the pressure, right? In terms of the pressure force. So let's keep this in mind and let's combine it now back to our production, right? So that was a part of a part, right? So this is a part. This is a part of this part, which is a part of the bigger picture right here, work, right? Minus work, because this is the work done by the system onto the surroundings. So we have this term, which we will nicely nestle right into here. So this is the rate of energy production within the system. Great. Now let's keep going. So we have, this is the same thing just copied over from the previous slide. We have this very long statement, right? So let's see how we can simplify it further. So as we can see, we have both of these terms with the same integral and then we can also see velocity. We can see the normal vector right over here. The only thing that's missing is this side is missing the density, right? So what can we do to actually combine these two terms and make this a little more simpler? The easiest way is to multiply this term by density over density. And that's just one, right? So it doesn't impact this statement at all. So we're going to multiply this by rho over rho. And what you'll see happen is because there's rho as a numerator and then rho as a denominator, which we can move right under here, this pressure. So pressure divided by rho, we'll see it in a second. We can easily combine these two terms. So this isn't energy, but it's part of the work. So that's where this term comes from, as we were kind of wondering earlier. And then we have rho times velocity and the normal vector, and then the area, cross-sectional area. And then we have right here, QS, Qgen, and then minus the work of the shaft, right? So this is, in conclusion, this is the conservation of energy statement. So how do you go about applying this? Well, there are a lot of things that we won't need in each question or scenario. So just being very aware of what you can cancel out, having a really good rationale for it, really understanding each component will set you up for success. So just try to understand every part of this and know that you won't need all terms in this statement. So if you have any questions, just come to my office hours. I'm more than happy to help. But thanks for watching this explanation of the conservation of energy. Thanks.